let's use calculus to prove that the area of a circle is pi r squared. Very exciting. Now, this is actually going to go beyond sort of the scope of the AB calculus material. Okay, but I think it's really exciting to explore anyways. So you can, it's just a cool application. And we're going to look at more than one way of doing it. Okay, so the first way, I want to use sort of the traditional area under the curve. Okay, so how do we set that up? Okay, well, we've done that with x and y coordinates. So you make an x and y coordinate, right? You make your circle. And you need to practice my circles. You need an equation, x squared plus y squared equals r squared. Now, what I like to do here is sort of to limit like the amount of plus and minus, you know what I mean? Like it's y equals plus or minus the square root, and then we've got positives and negatives. Let's just do this. Let's say, you know what, this is clearly symmetric, right? Circles are definitely symmetric. And we're only going to look at the first quadrant. So our sum is going to be just this first quadrant, and then we can multiply it by 4 to get the total area. Okay? So what we need to do there is we're making Riemann sums. Our dx's, right, our differentials are going to be horizontal, so it's dx. And so we're going to solve for y. We get y equals the square root of r squared minus x squared. Now, the next thing we need to do is to actually set up our integral. And because we've got to multiply it by 4, we're going to put a 4 out front. So it's 4 times what? Now we're integrating, just look at the one quadrant. X goes from 0 to r. So it's from 0 to r. R is the radius. Our function is r squared minus x squared. And then dx. Okay? That integral will give us the answer. Now, excuse me. How do we integrate this thing? Not obvious. So, based on the methods that I've discussed so far in this video series, we don't actually have the tools to do this. The issue is, like if you're thinking about a substitution, by the chain rule, you know, there's some derivative, but if you multiply, like thinking what the derivative is, you're gonna have, you don't have a 2x. You need a 2x there, and then you could do it. We don't have it. So the strategy here is actually trig substitution. Sine squared plus cosine squared is 1, or you could say multiplying everything by r squared, you know, if you do r squared sine squared plus r squared cosine squared equals r squared. And so the substitution that we want to make is we want to say something like x equals r cosine theta. Okay, so let's make that substitution. Say x equals r cosine theta. Now, note that cosine theta, when theta is 0, okay, x is 1. If you're just looking at x being cosine theta. So x typically goes with cosine theta, and when we make that substitution now, what happens? Okay, we're switching to theta, okay? And if we switch to theta, now, in terms of theta, the angle, we're starting at 0 still, but then we're going around to all the way up to pi over 2. So now it's from 0 to pi over 2, because we're living in the theta world. And then what do we end up with? Well, we've got to say what dx is. So dx equals certainly r sine theta, d theta, right? You need the d theta in there. And so now let's substitute in, see what we have. We've got r squared minus, we're going to square this, r squared cosine squared theta, and then dx is r sine theta d theta. Okay, now this might look more complicated, but it's actually going to, I think, not be. Okay, theta is all we're integrating. So what we can do here, we can factor out an r. You factor out the r squared, but the square root of r squared is r, so when r goes out here, we can take both of these r's and just put them outside. So we get a 4r squared. This is going to stay 0 pi over 2. And then what are we left with? We're left with 1 minus cosine squared theta But that's sine squared theta, right? The square root of sine squared theta is just sine theta. So you get a sine theta in there times another sine theta is just sine squared theta, d theta. Okay, so it simplifies rather nicely. But once again, we're actually a little bit stuck because you can't just integrate that straight out. So what do you need? It's another trig substitution. And when it comes to sort of trig substitutions in general, for calculus, the two that we're doing are actually the biggest two. Sine squared plus cosine squared is 1, is sort of like the main one. We just did that here. When we pull out the r, we get 1 minus cosine squared theta. That's sine squared theta, right? It's again, why? Because we've got, just write it up here, sine squared theta plus cosine squared theta equals 1. Okay, the Pythagorean identity. Okay, we used it here. And so when it comes to circles, if you have squares, it can be helpful to substitute in, say, for x to be cosine theta or r cosine theta. But the second one for calculus is to get out of the squares. And there is a trig identity for that. So here it is. Okay, we keep everything. But now sine squared is equal to, let's get it in some different ways. It's often written like this, 1 minus cosine 2x, in this case theta, 2 theta over 2. Hopefully, like at this point, you see why this is so valuable. Because now, right, we're not dealing with, like when you're dealing with a square, you have problems in integration with trig because it's not sine cubed over 3, because if you take the derivative, yeah, you get the sine squared theta times cosine theta. There's no cosine theta. But when you have single powers, it's fine. So, what's next here? What I'm going to do is maybe pull out the 1/2. We're just going to get the cosine 2 theta by itself. So we pull out the 1/2. Now if you pull out this 1/2, okay, this becomes 2r squared. So we got the 0 to pi over 2. Pull out the 1/2, so this becomes 1 minus cosine 2 theta d theta. And now we're ready to integrate. Okay? But the parentheses are often omitted here because it's just obvious, right? Okay, so finally, so we've got the 2r squared, will stay out. And what do we have? So this is going to be theta. And then let's carefully integrate cosine 2 theta, right? So it's going to be, derivative of sine is cosine, so it's going to be minus sine 2 theta. But there's no times 2, so you have to compensate for that with the 1/2. So it's minus 1/2 sine 2 theta, evaluated at pi over 2 and 0. Now, you can sort of quickly check this because if you take the derivative here, right, derivative would be just cosine 2 theta, but times 2 and the 2 would cancel. Okay, so this looks good. So now, what's left? Okay, look at the 0 here. The sign of 0 is 0, if theta is 0, it's 0. The 0 doesn't contribute anything. Additionally, if you look at the pi over 2, and you do sine of pi, that's also 0, so that doesn't contribute. So all that contributes is this theta at pi over 2. So you just put in pi over 2. And if you put in pi over 2 for theta, you get that this is 2r squared times pi over 2, which is simply, of course, pi r squared. Okay, so there is a really nice sort of traditional calculus style proof that the area of a circle is pi r squared. I will add here a little historical aside. So Archimedes basically derived that the area of a circle is pi r squared by sort of taking a bunch of polygons and like getting the area of the polygons and looking at what happens as you have more and more polygons. It's not considered a formal proof by today's standards, but it was known that was true in the time of Archimedes. So there's some other cool ones, and let me show you another one. So for this next proof, we're going to do something a little different, and what we're going to do is consider the following. So you have like a dot here in the middle, and you have like a tiny circle that goes around it. And you got a bigger circle that goes around it, and a bigger circle. In effect, you have these concentric circles until you get your desired circle with a radius, say, of r. Now, in this case, we're going to exploit the idea of integration to get this area. Because the idea is this. If you basically look at the circumference, okay, of each of these circles, and you keep spreading out all these different circumferences, you can add up all the circumferences to get the area, okay? How do you add up all the circumferences? This is what integration actually is. So you're starting at the circle that has no radius, right? Like, I mean, it has no circumference, okay? And you're starting with 0, okay? But what you're doing is you're basically, think about it like this. These are all like differentials. Each time you go out, that's a new differential. It's a new dr, okay? You're successively taking more and more drs, okay? And so you're starting at 0, and you're doing all these drs until you get to the radius that you want, and we'll call that big R, okay? Now, so we're summing a bunch of what? We're summing a bunch of 2 pi r's, okay? Right, a bunch of circumferences, but we're summing them over like this, over a bunch of drs, right? So, and the drs are what goes from 0 all the way up to big R, okay? So, it's a little different style, okay? It's not an area under the curve. What it is, it's a summing of 2 pi r's, the summing of the circumferences, okay? And the piece that you're actually adding, right, is drs, right? Those are the tiny pieces. Like here, you're adding all these dx's, right? The dx's go from 0 to r, how we started it. We switched it to d theta. So now we're adding a bunch of like little d thetas going from 0 to pi over 2. So now we're adding a bunch of little drs going from 0 to capital R. Okay, so if we integrate this thing, this is kind of nice because we get, voila, pi r squared when you integrate, right? The pi can, however you want to look at it. The pi comes out, you know, the derivative of r squared is 2r. So it's pi r squared, evaluated from 0 to big R. And I made it big R to keep the variables different, you know, but if big R is the radius that we're looking for, then we get that the area is simply pi r squared. Okay, so that's another really cool and simpler proof, and hopefully that helps you a little bit with some of the ideas of integration. Now I do want to show you one more, and this is sort of interesting too. Okay, so if you have a circle and you subdivide it, let's do it like this, to quarters and then eighths. Now, what you would actually do is subdivide this an infinite number of times, right? But what you do then is you sort of like stretch it out. And you end up with all these pieces. And so the pieces basically go something like this. There's one piece, but then you match it with a piece here, see? And you keep doing that, okay? And try that again, make it look a little better. Okay, so you end up with a piece here. Sorry. I'm doing a specific style. Get a piece here. Okay, and then I think that, yeah, the top here. You get a piece here. Here. You just keep doing this, right? And so when you do this, see, basically what you're doing is you're stretching these out, and you know you wouldn't stop with it, right? You would just keep doing this. I'm not going to bore you with my drawings, however. Are we close to being done now? 1, 2, 3, 4, 5, 6, 7, maybe one more. Okay, what do we have here? We have the circle sort of like stretched out into all these different pieces. Now, what's what? Okay, so if we look at this, this is R. Okay, that is R. And, right, that's just one of the sides here. Okay? You see that? And then what's the rest of it? Okay, well, the rest of it is basically you're summing this, right, because it's in effect half of the circumference. Half of it goes to the bottom, half of it goes to the top. Okay? So both of these two proofs, it's assuming you know the circumference. And so what's half of the circumference? Half of the circumference is, well, 2 pi r is the circumference, or half of that is just pi r. Okay? And what you have here, basically, you have the area of a rectangle. Now, they might be like, what? How is that the area of a rectangle? The issue is that we have a finite number here. But if you have an infinite number of these things, right, they do collapse to sort of like verticals, okay? And so this is not really a formal proof, but it is a classic proof that is sometimes shown to say that it's simply the area of a rectangle. And so we have the area here is pi r squared. Let me write it in here too. This is the area. So the area here is pi r squared. Here we have capital R. Here we have little r. This one, we also had a little r. And so this is actually the area, right? This is the area. Okay, so hopefully this was a little fun, and you can start to see some of the powers of calculus, kind of the idea of looking at, say, circles in different ways. And I really want maybe you all to focus on this one, because if you can understand this one, that'll go a long way to sort of understanding the idea of integration. Because integration goes beyond like a particular technique. I mean, this is cool, right? It works well, it's a nice technique. But how much more elegant is this? It works, and it's exploiting, and you'll learn more about sort of, when we do volume, you'll see integration, I think, in a broader light. But for now, right, just to recap, it's this idea of you're summing a bunch of circumferences, right? It could be summing a bunch of anything. And the key is when you sum them, you're summing them like going out to the right. When you go out, you're getting bigger and bigger radii. But there are a bunch of little drs that go from 0 to big R. Okay? So the area is pi r squared, no matter how you look at it.